Hi everyone, my name is Junyoung Lee from DG South Korea. I will introduce our work, Diffusion-based generative system surrogates for scalable learning-driven optimization in virtual playground. The increased complexity of modern computer environments poses significant challenges to traditional methods. These challenges can be grouped into three categories. First, data collection constraints. Physical systems often impose strict limitations on sampling rates or introduce considerable overhead. Second, vast configuration spaces. Heterogeneity and scale in modern environments lead to enormous configuration spaces, rendering exhaustive searches impractical. Third, system responsiveness. High resource utilization or frequent reconfigurations can degrade performance or cause instability, making it difficult to keep the system responsive. Other fields extensively leverage data obtained from virtual environments. In these settings, surrogates explore a variety of behaviors to efficiently gather training data. This approach overcomes both physical and temporal constraints. However, there is still insufficient research on using these kinds of methodology in computer system optimization. We propose DeepNest, which builds a surrogate-based environment and applies it to accelerate traditional system optimization technique. Recent generative model research increasingly employs diffusion models to create images, videos, and time series data. A diffusion model consists of two processes: a forward process that gradually adds noise to an original image, producing a random noise image, and a reverse process that learns to remove this noise and recover the original image. Diffusion models offer several advantages, including stable data generation, high-quality samples, and flexible conditional generation capabilities. We intend to use a diffusion model as our surrogate. As shown in the figure, we generate high-fidelity data from pure noise, which we then use for system optimization. To achieve this, we modify the internal architecture to be optimized for 1D data and retrain the model. We also incorporated an outpainting approach to enable continuous data generation by using previously generated samples as context. As shown in the figure, each newly generated segment is conditioned on both the preceding output and condition components. This sequential process allows the model to produce data in a step-by-step fashion, effectively painting beyond its initial output. By supporting such flexible conditional generation, the model can create the data with diverse distributions tailored to specific needs. Consequently, users or downstream systems can generate data they require simply by adjusting the context or condition inputs, which is advantageous for dynamic system requirements. We visualize the data to check the visual quality of generated data. Each group means that we give same condition to generate data. As we can see, although the condition was same, DeepNest can generate a variety of data which enhance diversity of samples. We also visualize the outpainting results. The figure shows that even with the same initial context and conditions, the model generates diverse data samples rather than identical outputs. We also apply DeepNest framework on real-world optimization problem, cache allocation, with reinforcement learning. We ran 5 benchmarks on each core and trained cache allocation policy using DeepNest and traditional RL algorithm. As illustrated in the right figure, the policy trained with DeepNest can reach high rewards compared to traditional RL algorithm and non-cache allocation setting, showing that DeepNest can provide high sampling efficiency and diverse data generation. Thank you.